Hello, welcome you all for another session on module number 1. Today we shall have an introduction about thermal stresses. What do you mean by thermal stresses? We all know, we all keep talking stresses. I am severely stressed. I have been severely loaded, something like that. Imagine yourself that you have to submit a couple of assignments and you also have to attend your personal very urgent work. All that you have to do it, say complete it by tomorrow, everything. I hope you all feel that you are loaded. Yeah, that's what. So if you have load, then only you will be stressed. So similarly, if I have a bar, if I don't apply any load on it, then that member is not going to be stressed. Please remember, the stress will be there only when, say, either one or a member is loaded. Okay, now we are going to talk something about what are called as thermal stresses. Okay, thermal means heat. Okay, the amount of heat in the body is probably indicated, represented by what is called as the temperature. The temperature is the representative of the heat content in the body. Okay, so we all have learnt maybe in our school days itself, when we add heat to a body, its dimensions are going to increase. If we remove heat, if we cool the body, removing the heat is same as cooling the body, then its dimensions decrease. Okay, then as the heat is increased into the body, then the volume of the body is going to change. That is basically the change in the dimensions. Now we are talking module number 1, which deals completely with respect to only one dimension, that is nothing but a bar. So similarly, the thermal stresses also we discuss with respect to a bar. Say bar means a long body whose cross-sectional dimensions are very small and subjected to axial load, and that is basically called as bar. Okay, we are talking about, say I have a wife. Okay, I have a wife. Okay, before I go to what is called as alpha coefficient of linear expansion, I have something, introduction. Okay, thermal stresses. So I have a bar. Say it is at some temperature, room temperature, say 25 degrees centigrade. And because of some reason, and it has been heated and its temperature has risen to 40 degrees centigrade. Then naturally 25 degrees centigrade, 40 degrees centigrade, some heat has been added. Okay, so what is the effect of this heat? So heat is also a form of energy, and you all know that energy or work is basically, in crude words, it is equal to force multiplied by displacement. So whatever the energy you have, you definitely must have some force and displacement, and therefore this thermal energy, heat energy, this also has something to do with force. So here also we are going to have some load. Under what circumstances we are going to have load, and when we do not have load, though the temperature has changed, all that we shall discuss under this topic. Thermal stresses. When do you have thermal stresses? Then how much is that? Then is it tensile stress or is it compressive stress? All that we will be able to answer at the end of today's lecture. Okay, so what do you mean by thermal stresses? The stresses induced in a bar because of the change in the temperature. Those stresses are called as thermal stresses. Thermal stresses are the stresses induced because of the change in the heat content of the bar. Okay, and so those stresses are called as thermal stresses. Okay, we have understood what is thermal stresses. The change in the temperature sometimes induce stress in the member, stress in the bar. Those stresses are called as thermal stresses. Okay, now before I really go to how to calculate those thermal stresses, I have another topic, what is called as stress alpha. Please go back to your school days, or at least in PUC, I am sure you must have come across, this is what is called as alpha. This is called as coefficient of linear expansion. It is basically a property of a material. Please remember, here we are not discussing heat transfer or anything. So we are dealing with heat transfer of a solid body only. And okay, so that too, solid body doesn't mean that I have a plate or anything. I have a bar like, say, wire like material, okay, wire like member. And that, okay, alpha is what is called as, it is a material property, it is called as coefficient of linear expansion. Okay, let me explain for a bit. So imagine that I have made of a wire of say aluminium. Okay, this is aluminium and its length say is say 1 meter, and right now its temperature is T1, and I increase its temperature to T2. Let me assume that T2 is more than T1, and therefore immediately I should call it as what is delta T. Delta T is T2 minus T1, so many degrees centigrade. This is the temperature change. Okay. So when the temperature changes from T1 to T2, okay, so its length is 1 meter at the temperature T1. Please remember, when the temperature changes to T2, are you sure? Do you agree that its length is going to increase? Yes, its length is going to increase. It is going to be at T2 degree centigrade. It is more than 1 meter. Okay, so then I shall find out what is the change in the length, delta L. Okay, I can easily do it. Okay, T1 say 25 degrees centigrade, T2 say 50 degrees centigrade. Okay, let me take this. T1 25 degrees centigrade, T2 say 50 degrees centigrade. So I can find it out. So what is the length? That is what I call it as the change in the length. Okay, so the area of cross section is immaterial. So whether it is a 10 millimeter square or 20 millimeter square or 30 millimeter square. So on this alpha value, okay, the area of the cross section of the wire is not going to matter. Okay, if instead of 1 meter, and if I take it something different, say it is 1.5 meters, okay, again 25 degrees centigrade, then I increase to 50 degrees centigrade, okay, again its length will increase. When the temperature will change, its length is going to increase, and here also I can find out what is delta L. Okay, what is this delta L? How this delta L, how they are related in general? If I make it in general one, say its length is L at a temperature T1, L at T1. Okay, then I shall change the temperature and let me assume that it becomes say L1 at temperature T2 or L2 at L1 at T1, L2 at T2. Okay, now, so what is the change in the length? Say this delta L, which is nothing but, this is nothing but L2 minus L1. So L2 minus L1, if T2 minus T1 is positive, L2 minus L1 is positive. As the temperature increases, okay, the length will increase, otherwise it will decrease. So now, how is it related? On what factors is it related? Delta L shall increase. It depends upon what is the material. So if I do the same experiment for copper or aluminium and different steel, different wires, every time delta L is going to be different. Though you have the same temperature T1 and T2 and the same length, but materials are different, and therefore, then what is the value of alpha of that? Okay, it depends. Delta L depends upon what is the material, that is nothing but, that is what is alpha. Then what is the value of the initial length of that, and it also depends upon what is the change in the temperature. Or in other words, alpha I can write it as alpha is equal to what is delta L divided by L1 into delta T. So the coefficient of linear expansion is defined like this. Okay, can you define it? Alpha is equal to delta L. Alpha is equal to delta L. Please remember each term. What is this? Alpha is coefficient of linear expansion. What is delta L? The change in the length. What is L1? The initial length. And what is delta T? The change in the temperature. Okay, so making use of this. So alpha E is equal to delta L. when L1 is 1 and delta T is 1. So can you define alpha now? Alpha, the coefficient of linear expansion of a material, is the change in the length. Is the change in the length per unit length of the material. Per unit length of the material. Per unit length. Any material we do not use it. Per unit length. L1 is 1. Per unit rise in temperature. So if delta T is 1, L1 is 1. In that case, alpha is equal to delta L. That is what is called as coefficient of linear expansion. So how much length change? Okay, what is the change in the length of a wire? That can be easily found out. Okay, if the length is if the temperature changes by delta T, if the temperature changes by, from the same expression I can write down what is called as delta L. What is that delta L? The change in the length. This is equal to alpha into L, the initial length. This into delta T. So delta L into alpha into L into delta T. This is what I call it as free expansion of the wire. Of course, it can be free contraction also. If delta T is negative, then delta L also is negative. That means the length is going to decrease. Free expansion, assuming that delta L is positive, or it can be free expansion or contraction. Okay, whenever I write this delta L, by calculate this, immediately I shall call it as either free expansion or free contraction, depending upon what is delta T. If delta T is negative, then it is free contraction. If delta T is positive, then I call it as free expansion. And most of the problems we have delta T positive, and therefore we will be coming across what we call as free expansion. That means I have a wire, this is a change in the temperature. Okay, if everything is fine, if it is allowed to undergo freely the expansion, how much it would have expanded? That is what is the meaning of that. Okay, free expansion. I hope you have understood this. Okay. Now, what do you mean by thermal stresses? Thermal stresses are the stresses induced because of the change in the temperature. So when I say change in temperature, that means the change in the heat. That is understood. Okay. So now, whether thermal stresses are induced when, immediate question, does it mean that whenever there is change in temperature, the member is subjected to thermal stresses? Okay. Does it mean that? Okay. So it is not. So it's just like, say I have, what is this? Imagine that it is a circular one and its cross section say is 100 millimeter square. And say its length is say 1 meter. Okay, what is this? It is all solid and this is the axis. Okay, what is this? I cannot call it as a bar, okay, because I have not applied load. If I apply load on the axis along either a tensile load or a compressive load, then I call it as bar. Okay, if there is no load, then I can say that it is a circular member having cross-sectional area so much and the length of so much. Okay, so I just call it as a member. It is not bar. Okay, in our mechanics of materials language, bar is a long member having smaller cross-sectional dimensions and please remember subjected to axial load. If there is no axial load, then we can't call it as a bar. Okay, so now I have a member like this. Okay, so I ask you to calculate what is stress in this member. Okay, first of all, the question is hopeless and it is meaningless. So what is the meaning? Why it is meaningless? First of all, stress at what point? You have to say stress at what point? Stress on what plane? Okay, then the question of calculation of stresses will come into picture only if it is loaded. If there is a load, if you have force on the member, then only. So as you can say that it is not subjected to any load and hence there is no question of stress. Okay, so please remember this. This is very important for us. if the member is not subjected to any force, then it is not subjected to any stress. Okay, so now I shall go on to a similar thing and extend it for what is called as thermal stress. So again, what is this? It is a circular member again, and probably feel that it is a cross section in a circle. Okay, it is a circular member and its length say is L, and it is made of a material, okay, whatever it may be, and whose alpha is so much. Alpha is so much. What may be the unit of alpha? What may be the unit of alpha? Go back to the definition of alpha. Alpha is equal to delta L divided by L into delta T. Okay, so alpha, what is delta L? Delta L, a change in the length which may be millimeter or meter or centimeter, and divided by L, the length again, which may be millimeter, meter, etc., millimeter, and delta T, degree centigrade, change in the delta T, T1 minus T2, T1 is in degree centigrade, T2 also is in degree centigrade, T1 minus T2 is not unitless. Okay, it is this thing, and millimeter cancels, so many per degree centigrade, that is the unit of alpha. Okay, so alpha, so this also is made of a material whose alpha is so much. This value is quite small, okay, usually something into 10 raised to minus 6 of the order of that. Okay, I know L, I know alpha, I also know delta T. What do you mean by delta T? Delta T I know. So I know what is the temperature. Then after some time, after supplying heat, then what is the new temperature? I know T1, I know T2, T2 minus T1 is so much. This also I know. It's per degree centigrade, this is so many degree centigrade. Okay, so I ask you, what is the stress in this? Okay, again it's similar. Please remember, stress is going to come into picture only if it is subjected to any force. If you don't have any force, then there is no question of stress. So now immediately what I can calculate, what is the free expansion of this? Free expansion of this member. Okay, how much is that? This is equal to alpha into L. L is nothing but L, the initial length. And what is delta T? Delta T. So this is equal to so many millimeter. Okay, so as it appears that, okay, its length is no more L, it is going to increase. Please remember, delta L is very small. Okay, it is in the form of a fraction of a millimeter. But if I show that with this scale and this thing, then I won't be able to show delta L, and that is why to make the things clear, I have shown as if delta L is quite large. Okay, its length will increase. Okay. L, earlier it was L, now its length is L plus delta L. At temperature T1 it was L, at temperature T2 it is L plus delta L. Where is the question of stress into? Okay, this length, whatever it is allowed to undergo, and the member of the bar, I don't call it a bar, the member is allowed to undergo expansion freely. No restriction, nobody has stopped it. If nobody has stopped, then there is no question of stress in the member. Okay? So now the question of stress will come into picture only when if the free expansion, or it is true with free contraction also. Expansion of a member because of the change in the temperature, or contraction of a member because of the change in the temperature. If you are not going to allow it, if you are going to restrict it, if you don't allow that to happen, then only the stress will come into picture. Thermal stresses are induced when free expansion or free contraction is prevented. So what I mean, okay, how do I prevent this? For example, so imagine what I also have this side also. This side also I have what is called as a wall. This is in our mechanical engineering, the meaning of this hatch line frame, what is called as frame. The frame is the one which is imagined to be a rigid body. it will not undergo any kind of motion or displacement. Whatever the amount of force you apply, it will undergo zero change in dimension. So therefore, now let me come into picture. Okay, so for a while, okay, I have wall this side and also I have wall this side, and this is the bar, its length is here and it is at temperature T1. Now the temperature has changed to T2. For a while I imagine that this is not there. This is not there. Then what would have happened? It would have increased its length by this much. Okay, that is delta L is given by this value. Okay, so now let me come to the real case, real situation. What is that? This delta L, which would have been increased, okay, that is not allowed. Okay, therefore the wall which was there now I shall bring that wall here, okay, and that wall will push this member. The wall will push this member. It is as good as subjected to a force. I apply this wall, since it is not allowing this length to be increased, okay, it is as good as I am applying a force. Okay, how much force? This force P is responsible for contracting so much. Okay, what kind of stress is subjected to now? The stress is compressive stress. I am answering the third part. If it is, the temperature is increased, then the length is not allowed to increase. That means that member is subjected to compressive stress. Okay, so I have answered when thermal stresses are there. If the free expansion or free contraction is prevented, then we have thermal stresses. Then what time? If the free expansion is prevented, then I have compressive stress. If free contraction is prevented, then I have what are called as tensile stress. Okay, then how much? How much also is very simple now. The force P. If I have force P, then P divided by A. Or in other words, this force P should be able to contract this much. What is delta L? Delta L is alpha L into delta T. This is also equal to P L divided by A into E. What is A? A is the area of cross section. Okay, what is E? Young's modulus of elasticity. What is L? L is the length of the member. So you know L, you know A, you know E, you know all this delta side. You can easily calculate how much it is P. So P is so many Newton. What type of force is this? This is compressive in nature. So I want to know what is the thermal stress induced. Thermal stress, sigma, normal stress. So it is compressive in nature. So P divided by area, and inside bracket I write compressive. Another way is, if you don't want to write compressive, then you write it as minus. Why minus? Because it is compressive. Minus P by A. Okay, this is how we calculate what is the stress. Okay, I have another situation, slightly different now. Similar problems are there in the question paper also. I have a bar. Okay, so what is this bar? This bar is of length L. It is made of a material whose Young's modulus is E. It is made of a material whose alpha is so much. So all these are known. These are known. Then what else I know? I also know what is T1 and I also know what is T2. These are also known. These are also known. Okay, if the member is like this, then even if the temperature increases, okay, then it is allowed to undergo free expansion, and therefore there is no question of stresses induced. Okay, so but I have a wall here. I have a wall. The wall is not at the end of this bar. There is some gap here. There is a gap. This is delta. Okay, so this delta also is known. I know delta, I know, okay, L, E, A, E, alpha, T1, T2 and delta, all of them are known. Okay, delta value is also given. Okay, so then what is the question? The question whether the member is subjected to any stresses or not. Whether the member is subjected to any stresses. Okay, how do you check? When thermal stresses are induced? If you, okay, in this case T1 and T2, assume T2 is more than T1, then if free expansion is prevented, then only thermal stresses are induced. My first question for this is whether stresses are induced. Okay, for that to answer, I have to calculate what is free expansion. I shall calculate what is free expansion, which I call it as delta L. How do you calculate it? It is alpha into delta T, alpha into L into delta T. You know alpha, you know L, you know delta T, as you know all this. Therefore, you will calculate what is the free expansion. Okay, so then I shall calculate delta is delta L less than alpha. So that means the free expansion delta L, it will come something like this and it is not yet touching this wall, something like that. If delta L is less than alpha, then is anybody preventing the expansion of that bar? Because delta L is less than, not alpha. Delta L is less than delta. Delta L is less than delta. Okay? So this length, whatever is the increase, if it is less than delta, what is your answer? If the free expansion is less than that gap between the wall and the bar, okay, then whatever this delta L is not at all prevented, it can undergo, and we shall not have any stresses. No stresses. We shall not have any stresses. If delta, when this is true, up to equal to delta also. But if delta L is up to equal to delta, then also we don't have stresses. If delta L is greater than delta, then we have stresses. We have what type of stress? So it is, this wants to go beyond this wall, and the wall is not going to allow it. Okay, this bar wants to cross this. The wall is there and it is going to apply force now. When it tries to go beyond this length, the wall will apply compressive force, and therefore what is called as, we have compressive stress. Then how much? Okay, so how much it is prevented? How much expansion? Please remember, up to this delta L is more than delta. This delta L probably, say, would have gone something like this. This is your delta L. This is your delta L. Out of this delta L and this much delta, it is allowed. You don't have to apply any load and that much. Okay, for that you can have free expansion. Then for how much expansion the load is going to come into picture? That is nothing but this minus this. That is nothing but only for this much. But how much is this? This is nothing but delta L minus delta. Delta L minus delta is the expansion which has been prevented. Delta L minus delta is equal to P into L divided by A into E. So knowing all this, what do you get? You can easily find out P. This is known, L is known, A is known, E is known. Then P you can easily find out. Then you can find out what is sigma. Sigma is equal to P divided by A, so many Newton per millimeter square, and immediately write down what is called as compressive. Okay, this is what exactly like this you will have seen questions appearing in the question paper, and very simple. And with this background, now we can take up any problem on thermal stresses. I think that I shall do it in my next class. Okay, all the best.